Hi guys. So today I have a doctor's appointment, so I'm gone. And you have a substitute teacher, so you should be watching this in class. But I'm gonna go through everything as if I was there with you. The substitute will just need to pause and unpause the video so that you guys have time to gather your supplies and such. So the first thing that you'll want to do is make sure that you have your note-taking supplies, scissors, taper glue, markers if you use them, and a calculator. So pause the video right now so you guys can go and get your supplies for your table. And then I'll show you what we're gonna need for today's stuff. So now that you're ready to take notes, here's what we've done so far for chapter 1. We've done these notes and we've done these homeworks. We only have one homework assignment left, and it goes with these two notes. It's kind of a tricky one, so I don't want to do it like over a video while you have a substitute. So what we're actually going to do is we're going to skip, do those later. And today we're going to do notes 7 and 8. Does that make sense? So we're skipping around a little bit and we're going to do these two notes today while I'm gone, because they're a little bit easier for you to follow with the substitute. So what I would do in your notebook is just skip a page, leave a page for notes 5, and then leave a notes page for 6. Does that make sense? So what we're actually going to be starting with here is the next page. And let's see. That one's going to be called Precision versus Accuracy. Here are all of the cutouts that you are going to need for today. This one is going to go in the Precision versus Accuracy page. And this other one, these two, are going to go in the density page. So pause this video and cut these out. I'll show you where they belong in a moment. So here are the pages. Precision versus Accuracy. This is notes page 7 because we're skipping. I just put that up top. And then over here, density. This will be notes page 8. So pause the video if you need to glue these in. Precision versus Accuracy, notes 7, notes 8, density with the cutouts. Now, the reason we're doing both of these topics today while I'm gone is because they're fairly simple, and I know you can do it without me. So precision and accuracy are just two words that people get confused a lot. They'll say like, oh, it's like really precise. Oh, it's like really accurate. But those mean two completely different things when we're working in science. So precision, actually leave a couple of spaces here, skip some lines. Precision refers to how close the measured values are relative to one another. I like to think of precision as replicable. It's got the R in it. That's how I remember it. I can do it over and over and over again and get the same result each time. That means it's precise. Doesn't mean it's accurate though. Accuracy is how close your value is that you're measuring how close the measured values are relative to a standard or relative to what it should be. So this is like, are you actually getting the correct value or not? For example, gravity, you don't have to write this down, but gravity makes things fall at a certain speed. You can measure it. Physicists in Mr. Dittmer's class, physics, AP physics, they go and they measure gravity, and it tells you that gravity makes things fall at 9.8 meters per second squared. That's gravity. So if I do an experiment and I'm getting, I don't know, if I'm not getting 9.8, then I'm not accurate because that's what I should be getting. I might be very precise. Maybe I get 3.4, 3.5, 3.55. Maybe I'm getting like numbers that are very similar to each other. That would be precise. But if I'm not actually hitting the correct value for gravity, then I'm not accurate. Does that make sense? So here's the bullseyes up top. And the example that I just gave, if gravity is 9.8 and I'm getting 3.4, 3.5, 3.55, like my numbers are very close to each other. My darts, pew, 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 are super close to each other, but they're nowhere near where they should be. So in this target up here, what I would say is this one has, let me get a new marker. This person is not accurate. I would say their accuracy is very low accuracy, but they're very precise. Those dots, like, oof, very close to each other. So high precision, but not very accurate for what it should be. Now, if gravity was supposed to be 9.8 and I was getting 9.7, 9.8, 9.9, real close together and correct, that would be this right here. Boom, boom, boom. All three close together and on point. So I could say this has high accuracy and high levels of precision. This one here, we've got the darts are pretty spread apart if you look at them, right? But each one is relatively close to the bullseye, like that center ring. So I'm gonna say this one actually is pretty accurate. Like it is so close to being in that center ring. All of them are. but we have really low precision because we're not able to hit the darts in the same spot each time. And the worst combination of all of them would be not only, look at how far away, not only is it super far away from the center, but the darts aren't even close to each other at all. So low accuracy as well as low precision. So what you'll get on your test, which is next week, by the way, what you'll get on your test are some data values, and it will say like gravity is supposed to measure at 9.8 meters per second squared. When you perform experiments, you get, let's see, you get 7.6, 7.6, 7.5, and 7.4. It'll say, are you accurate? And you'll be like, no, because those are nowhere near 9.8. Are you precise? You'll be like, yeah, super precise, because all of those are like, oof, like within the same area. So it'll just ask questions and you'll have to decide, is it, high accuracy, low accuracy, high precision, low precision. So pause this if you need an extra moment to finish copying this down. Now underneath that, we're going to do a separate calculation for percent error. And what the percent error allows us to do is to decide how far off the values are from what they should be. So let me give you the formula first, and the formula is not going to make sense until we do a problem, but I'll still write it out. Just write it down. It doesn't make sense right now. That's okay. Number hypothesized minus number correct divided by the number correct. Put all of this in absolute value signs, meaning that like if you get a negative number, just get rid of the negative because we want it to be positive. And times the whole thing by 100. That's our formula. I'm going to elaborate a little bit on this. The hypothesized value is going to be what your value is, like what you are predicting or measuring. And the correct values are going to be the actual value that happens. Again, WTF, it doesn't make sense right now, but down below we'll do two problems and you'll see that this is actually a super, super easy calculation. Okay, so splitting the bottom of the page in half, just so we can do two problems here. I normally I weigh about 160 something, usually 165 pounds. That's like just my normal. And so now with this pregnancy, like I weigh more. So my driver's license still says I weigh 165, but I actually don't weigh 165, right? Because you're supposed to gain like 35 pounds when you're pregnant. So what would be the percent error from what I actually weigh to what my driver's license says. So that's the problem that we're going to do here. So Oliver's driver's license says she weighs 165 pounds. However, she's pregnant and actually weighs 'I weighed myself this morning so I could do the math with you today. I actually weigh 191 pounds. Woohoo! So doing great on my weight gain. So what we're going to do is okay, so the 165 is going to go here. And the correct, like the actual value that I weigh is 191. So we're going to take that and put it over the actual value, absolute value, and times 100. (165 minus 191 divided by 191). That's a negative number, so I'm going to times by -1 just to like get rid of that, and times by 100 to figure out that this is a 13.6% error. That makes sense? So it's not actually as tricky as it looks up here. You're just taking like the correct value, what I actually weigh, putting it here, and then the other one goes up front. So number 2, back when I was in high school, the coolest thing you could have was like an MP3 player, and you would download songs illegally, of course, because you didn't know how to do anything else. But I remember I got an MP3 player, the little iPod shuffle thing, and you estimate your new iPod shuffle will hold all 2,089 songs that you have illegally downloaded. Oops. However, when you tried to put them on the MP3 player, it only holds 1,944 of them. Probably because you had some like really long soundtracks or something that took up a lot of space. So in actuality, it only held 1,944. We thought it might hold 2,089, but it didn't. And that was about a 7.5% error on our part. Some people choose to keep the positives and the negatives in there. Like, remember that this one was a negative and we like took it out and this one was a positive. You can choose to do that. I don't really like to, but this would be saying, like, since it's a positive value, that the prediction was over how much it held. And this one is saying that like the prediction, like the officer that pulls me over would think I would weigh 165 based on my driver's license. The prediction is lower than what it actually is. So that's what it would be if you kept the positive and the negative sign there. But I like to take them out. So there is note 7, all done. Precision versus accuracy, percent error. So the next page that we'll do together today is going to be density. So pause the video, take a little break, whatever, like 2 or 3 minutes, and then we'll get started here with density. So the density is essentially like how dense something is. And actually, the reason I'm going to be gone for my, the reason I'm gone and you have a substitute is I'm going to get an ultrasound. The way that an ultrasound works is it's based on the different densities between like the baby and the mom and the materials inside of our bodies. So let me show you. So these are some of the ultrasounds from real shiny. I shouldn't have laminated these. These are the ultrasounds from a really long time ago, back when I was 14 weeks pregnant, and now I'm like almost 30. But there are light spots and dark spots. Let's see. Let me just get rid of the shiny here. Okay, so this isn't my baby. I just found a thing online, but you can see that there's dark sections and then there's really light sections. The wider the section is, the denser it is. So you can kind of see how like here around the outside, you can see the skull. Obviously the skull is really dense because it's made of bone. Also this big white line here is the spine. Again, bone, which is really, really dense. So things that are dense have a lot of mass packed into a tiny space. So let's go back to the notes. What we're looking at here is we have 2 different pieces of metal. We've got copper and aluminum. And I want you to graph the data points here. We've got mass and volume for each, putting mass along the y-axis. The mass is in grams, and then put the volume in milliliters over here. So pause the video, give yourself maybe 5 minutes to get all of these graphed. So something like this. And it makes sense that it's going to go through the origin, because if you have 0 volume, like if you don't take up any space, you're not going to take up any mass. So try and get those to go through the origin. And then maybe label them a little bit. This one was my copper line. And this other one here is aluminum. P.S. Your quiz on the periodic table is going to be next class period. So be sure that you are practicing the song. If you want, you can find it on YouTube. Just look up ASAP science periodic table. It'll bring it up. You don't need to know the formulas yet. Like copper was weird. It was Cu. If you just write COPPER, copper, you get your points. You just have to know where they go in a blank periodic table for the first 36 elements. So be sure to study that today or tomorrow, whatever, so that next class period, you're ready to take that quiz. So here are my points. Now, density is calculated by taking the mass of something and dividing it by the volume of space that it takes up. So we have a couple of different ways that we could calculate the density. We could just pick a point, like this first point. We could take 101. Let's see. We could take, what is the density of copper? Because it weighs 101.2 when it takes up 11.1 milliliters of space. This says it weighs, the density is 9. If I did the next point, it says my density is 8.7. If I did the next one, .8. So they're very close to each other, but the best way that I can find the density without having these fluctuations is if I were to take kind of the average of all of them. Same thing with the aluminum. So instead of just picking a specific point and doing mass over volume, what we're going to want to do in this case is look at our line of best fit, kind of going off of what we learned in that first homework assignment. Our line of best fit will take the average of the data. Since we put mass on the y-axis, if we do change in y over change in x, aka if we do rise over run, aka if we are calculating the slope, in this case, our slope is going to be the density because we've got mass over volume. Kind of cool. See why we set it up like that? So let's see. We'll calculate that out. But first, the question I want to ask is, since we're talking about graphs again, what is the relationship between the variables? The variables being mass and volume. Because if one of them goes up and the other follows, or if one goes down and the other follows, then we say that's a direct relationship. Obviously, there's more complications we could add, but just for my class, we're going to keep it easy. That if they run the same, it's direct. And if they run opposite of each other, then we're going to call it inverse. The more that I weigh, the more space I take up. So that is a direct relationship. And then down here, let's calculate the densities of each metal but instead of using a singular point, we're going to use the slope of the trend line so that it averages out the data a little bit better. So for copper, if I use the entire data set, the amount that I changed on the y-axis, which was my grams, I went from 101 to 373.5. So I rised 272.3 grams, because that's the units on the y-axis. Rise over run, the x-axis changed from 42.2, sorry, 11.1 to 42.2. So 31.1 milliliters. The slope, AKA density of copper, is 272.3 divided by 31.1. And like we were doing before, it was like 8-ish, 9-ish, but now averaging out all of the data, our slope, our density is 8.76 grams per milliliter. So if I had a milliliter of copper, it's going to weigh 8.76 grams. Okay, next to that, if I wanted to do the aluminum, change in y over change in x, change in y. It's 180. Change in x. It's 66.9. Oops. 180.2 divided by 66.9 equals 2.69 grams per milliliter. So if I had a milliliter of each, this one's only going to weigh 2 grams. This one's going to be 8.7 grams, right? So that's what it's saying. Copper is a much more dense material. Which is kind of cool because, like, since the slope is the density, check it out. This has a much steeper slope. Okay. And the steeper slope is showing that we have a higher density. Okay, so the last part here, so copper is the more dense material, aluminum not so dense, and we can see because our slope isn't as steep. But then my last question is, what if we were going to work backwards through these equations? And let's say that I scooped out a sample of 155 grams of each. So question, if you had a 155 gram sample of each metal, how much space are each going to take up? Because it's not like they're going to be the same mass and the same size. 1 milliliter here is 8 grams. 1 milliliter here is like 2. So we know that for copper, the density is 8.76, and that equals the mass divided by the volume. So if my mass is 155, solve for x to figure out the volume. So my copper scoop that weighs 155 is going to take up about 17.7 milliliters of space. What do you think for the aluminum? Because aluminum is less dense. It's kind of more fluffy. It's got more space. So this is 2.69 is the ratio. And if my scoop was 155 grams of that, I'm going to use y now. I'm going to use y as the variable, so it's not the same, x, y, whatever. Doesn't matter. Solving for y. This one will be 57.6 milliliters. So even though they weigh the same on the scale, 155 little scoops, this one's going to take up so much more space than this one because the densities, right? This is a more dense material. This is a less dense material. And again, sorry, let me fix this. Sometimes the projector, when the projector dies, then the video dies. So let me restart this here. And we're back. So, oh, maybe not. Let's see. Why is this being all funky? There we go. Sorry about that. So here are my slopes, the 17 and the 57. I used the slopes to plug in the 155. And since aluminum is a less dense material, it takes up more space. So here's the full page. Hopefully the recording, I'll have to go back and watch and see where it like cut off. But we'll talk more about density when I get back into the classroom. We also are pretty much at the end of the chapter. So if you want, you can look in your packet, the last couple of pages between the last homework assignment, 1.5, and the new stuff, like the new cutouts for module 2, there's a practice test in there. So for the rest of the class period that you might have, what I want you working on with this substitute is, are all of your assignments done? Do you have turned in specifically the homeworks are the ones I'm more worried about? Do you have those 4 homework assignments turned in, either to Canvas or in the basket? You can also, if you've turned in homework, this box right here has graded papers in it that if you turn them into the basket, I wrote on them, graded it, and they're in there. Obviously, if you turn it into Canvas, you'll just see my comments that are on Canvas. So you need to be working on homeworks that might be missing or correcting ones that you didn't do very good on, and then starting to work on the practice test. Excuse me. Keep in mind, if you're doing the practice test, that we did skip a few sections. So make sure that you skip around to do only the sections that we've already completed. Okay. Bye, guys.